Module 6. Using the SensorTile.box PRO in Pro mode. In this module, we will use the SensorTile.box PRO in Pro mode, use the high-speed data log function pack as an example of what can be done with custom firmware, capture some real-time sensor data, and use it to train a machine learning model for the LSM6 DSV16X sensor. The high-speed data log function pack provides a comprehensive solution allowing you to save data from any combination of sensors at up to their maximum sampling rates. We've already programmed the firmware to the board, and now we will use the Python scripts that come with the data log2 function pack to capture and analyze sensor data. Please make sure your sensor tile is connected to your PC. Make sure your sensor tile is turned on. The orange LED should be lit solid and the green LED flashing. We are now ready to enter the Python virtual environment to run the scripts. Open a new Explorer window and navigate to C:/STBox Pro Workshop. Double-click on the start_v.env.bat file to launch the command prompt within the Python virtual environment in the script example directory. The path in the terminal should be prepended by .venv in parentheses. Now launch the data logging GUI by running the following script. Python hsdatalog_GUI.py. The GUI will launch and you will be presented with the initial connection screen. It should show a USB connected device. If not, try clicking the double-headed arrow at the right to refresh. Once the sensor tile is detected, click the green Connect button. You'll now be presented with the data log GUI. On the bottom left side of your screen, each available sensor is shown, and most will be enabled by default. You can selectively enable and disable individual sensors, and you can configure the settings for each individual sensor for the logging session. For now, let's leave everything at the default. Click the green Start Log button at the top. The sensor tile will immediately begin streaming data over USB, and you will see the real-time data for each sensor in the plots on the right side of the GUI. Move the board around to see the data change. Now click the red Stop Log button at the top of the screen. The sensor data has been saved to a set of log files on your PC. Let's look at them briefly. Open a new Explorer window. Navigate to C:/STBox Pro Workshop. Open the data log2 folder. Then open the utilities folder. Next, open the hsdpython_SDK folder. Then open the examples folder. This example folder contains a variety of Python scripts. We've already seen the GUI, but there are other scripts for viewing the logged data and exporting it into other formats. You will also find here a folder named with the current date and time. This folder contains the log files that were created during our logging session. Open this folder. There are several files here. The two JSON files contain metadata about the logging session, and the DAT files contain compressed binary sensor data. There is one DAT file for each sensor that was enabled during the logging session. Let's now create a new custom log session to capture data and use that to train a machine learning model for the onboard LSM6 DSV16X sensor. Before continuing, let's delete the first log session to avoid any confusion later. Go back one directory in Windows Explorer to the examples folder. Then delete the folder containing the log files. Leave this Explorer window open as we'll return to it later. Now return to the data log GUI. On the left side, scroll down to the list of sensors, which is below the tags information panel. The first sensor listed is the LIS2 MDL magnetometer. Click the green button at the left side of the sensor name to disable that sensor. The green icon will turn off, indicating the sensor is now disabled. The corresponding graph on the right side of the GUI will also disappear. Scroll down and click the green button next to the LIS2 DU12 accelerometer to disable it. Leave the LSM6DSV16X accelerometer enabled. Then scroll down further and disable the LSM6DSV16X gyroscope, the MP23 microphone, the STTS22H temperature sensor, and the LPS22DF pressure sensor. You should now have only a single sensor enabled, the LSM6DSV16X ACC sensor. There should be a single graph shown in the right side panel. Now let's configure the LSM6DSV16X accelerometer. Next to the sensor name, click the down arrow. Several configuration options are available here. The first is ODR, which is the chosen sampling rate of the sensor. Click the down arrow for this field and change the setting to 30 to set the sensor to record data at 30 Hz. The second setting is FS, which is the selected full scale of measurement of the sensor in units of Gs. Click the down arrow for this field and change the setting to 2. All other settings can be left at their defaults. Now scroll up to the top of the left-hand panel and find the Tags Information section. We are going to capture 3 different types of motion for training our MLC model: stationary, movement, and shaking. To differentiate this data for the automated tools, we will use the tagging feature. In this panel, we can give each tag a unique name to make our later work easier. Click in the first tag field labeled SWTag0. Change this label to stationary. Change the name of SWTag1 to movement. Finally, change the name of SWTag2 to shake. Make sure to leave each tag disabled for now, and you can ignore SWTag3 and 4 as we will not be using them. We can now start the logging session. Click the Start Log button again at the top to begin a new log session using our custom settings. We see the real-time data being plotted at the right. We will capture the 3 types of motion needed for training our machine learning model. Let's start with the stationary condition. Hold the sensor tile steady in your hand. Toggle the slider for the stationary tag at the left side of the GUI. You will see a green vertical line in the graph showing where the stationary tag has been enabled. You want to capture about 30 seconds of data. Try to hold the board steady in your hand during this time. Once about 30 seconds have elapsed, toggle the slider for the stationary tag again to disable it. You will see a red vertical line in the graph showing that the stationary tag has been disabled. Now move the sensor tile around slowly. While moving the board, click the movement tag to enable it. A green line will appear in the graph showing the movement tag was enabled. Continue moving the board along each of the 3 axes of measurement for about 30 seconds. After about 30 seconds have elapsed, click the toggle button for the movement tag to disable it. You will see a red vertical line in the graph showing the movement tag has been disabled. Finally, hold the sensor tile in your hand and shake it vigorously. While shaking, click the toggle button for the shake tag. Continue shaking the board in various directions along each axis for about 30 seconds. Once time has elapsed, but while still shaking the board, click the toggle button for the shake tag. You've now captured all the data necessary to train a machine learning model to recognize these movement patterns. Next, we will create this model and will program it into the machine learning core in the LSM6ESV16X sensor so that it will automatically recognize these types of movement. Click the red Stop Log button at the top of the GUI. You can now close the data log GUI. Return to the Explorer window showing the examples folder. You'll see a new folder named with the date and time of when the log was taken. Let's rename this folder now. Right-click the folder and choose Rename. Rename the folder Workshop. The next step is to extract the sensor data from the files contained here. Return to the command prompt from where we ran the GUI script. Run the following command: Python space hsdatalog _to _uneco.py space -t space workshop. This command extracts all sensor data in the workshop directory and saves it to an output folder called workshop_exported. The -t option causes the script to separate the data by the tags that we used during the capture. Once the script completes, return to your Explorer window. You should see a new folder here called workshop_exported. Open that folder. You'll see 3 folders named after the tags we used: stationary, movement, and shake. Within each folder is a CSV, or comma-separated values file containing the extracted sensor data for the period of time corresponding to the respective tag. Now we will import this data into the UNeco tool, which we will use to create the machine learning model. Open the UNeco GUI tool. In the UNeco window, first click the checkbox at the bottom left that's labeled Communication with the motherboard so that changes to Disabled. Now in the search box at the top, type 16X. The search results will show the STEval MKI227KA. This is an evaluation board containing the same LSM6ESV16X sensor that's on our SensorTile.box PRO. Click this device to highlight it, then click Select Device. UNeco will show a new window with a warning that communication with the motherboard is disabled. This is fine, so you can click OK to dismiss this message. Click the MLC tab at the left side of the GUI. Now we will load the training data that we captured a few minutes ago. In the Log Data Pattern panel at the top, click Browse. Navigate to C:\STBox PRO Workshop. Then go to the Data Log folder. Then open Utilities. Then open hsdpython_SDK. Open Examples. Open your workshop_exported folder. Finally, open the stationary folder. Double-click on the stationary CSV file here. UNeco will display the data pattern. Below this table, we need to type a name for the class label. Type stationary in this box and then click Load. Now click Browse at the top again. UNeco will default to the last location used. Go up one folder and then open the movement folder. Double-click the movement CSV file here. Set the class label to movement and then click Load. Click Browse at the top once more. Go up one folder and open the Shake folder. Double-click the Shake CSV file. Enter the label Shake and then click the green Load button. We have now loaded 3 different classes of device motion. Next, we will use this data to generate the machine learning core decision tree. Click the Configuration tab at the top. Ensure LSM6DSV16X is selected and click Next. Configure the MLC to run at 30 Hz and click Next. For inputs, select accelerometer only. Then ensure that in the accelerometer configuration, the full scale is set to 2 Gs and the output data rate, or ODR, is set to 30 Hz. This matches the sampling rate we used when we captured the data. Click Next. For the number of decision trees, we can choose 1 here, as we are only differentiating between stable, movement, and shaking cases based on acceleration data alone. Click Next. The MLC operates on windows of data, the length of which is expressed as a number of samples. All statistical parameters in the decision tree will be evaluated for this time window. The window length can be from 1 to 255 samples, and the resulting window length will depend on the sensor data rate. A window length should be chosen which will completely capture the particular movement pattern of interest. Here we will choose the size of that window to be 30. Because our sensor data rate is 30 Hz, this represents a window length corresponding to 1 second of sensor data. Select 30 and click Next. The next configuration option allows you to choose from a selection of input filters. You can add high pass, band pass, or IIR filters to precondition the raw sensor data prior to its use in the decision tree. We will not be using any filters for this demonstration, so please select End Filters Configuration here and click Next. Now we will configure the particular statistical models, which will be used to classify the device motion at runtime. There are many options here, including per-axis signal mean, variance, energy, peak-to-peak, zero crossing, etc. For our case, we will use peak-to-peak to classify the device motion intensity based on a computation of the maximum peak-to-peak value of the overall acceleration vector during the evaluation window. Scroll down in the list to find peak-to-peak for ACC_V. Click the Enabled checkbox for this criterion, then click Next. You will now save this configuration and associated data to an ARFF file, which stands for Attribution Relation File Format. This is an intermediate file that will serve as the input to the decision tree generator. Click Browse. Navigate to C:\STBox PRO Workshop and name the file training.arff. Click Save. Then click Next. You are now asked to provide numerical values for each of the possible decision tree outputs. We can accept the defaults provided: 0 for stationary, 4 for movement, and 8 for shake. These values are output via one of the sensor status registers at runtime, and application code can use these values to determine instantaneous motion state. Thus, in this case, an output value of 0 would equate to the stationary condition, a value of 4 the movement condition, and a value of 8 the shake condition. Please leave the defaults as they are and click Next. Now click the blue Generate button to generate the decision tree using the parameters we have set. The decision tree information is shown in the box below. Examine this output and then click Next. The meta classifier feature allows for post-processing of decision tree results to reduce false positives. If configured, the meta classifier will count the number of times the decision tree makes a given determination and will filter the output until the decision tree makes the same decision for the number of times configured here. In this demonstration, we will leave the meta classifier set to 0 for all states so that the decision tree output will be updated immediately upon detection of a new state. Click Next. You will now be prompted to save the UCF file. UCF stands for UNACO configuration file. This file contains the raw configuration data that will be loaded into the LSM6 DSV16X sensor. Click Browse. Navigate to C:\STBox PRO Workshop, then give this file a name of training.ucf and click Save. Click Next. You will see a window that states that the MLC configuration has been saved. Click OK. We have successfully generated an MLC configuration file for the sensor. You may now close the MLC configuration window. Then close UNACO. Return to the command prompt and relaunch the data log GUI by typing python space hsdatalog underscore GUI.py. Click the green Connect button. You should still have only the LSM6DSV16X ACC sensor enabled here. Below this sensor, find the LSM6DSV16XMLC sensor. Click the down arrow next to this sensor to expand the configuration panel for it. In the Load Configuration panel, click the Browse button. Navigate to C:\STBox PRO Workshop and find the training.ucf file. Click on this file and then click Open. Now click the play icon in the Load Configuration panel. This will automatically enable the MLC sensor and load the MLC configuration that we created. You should now see two graphs on the right side of the GUI. Click the green Start Log button at the top of the GUI. The top graph will show the instantaneous accelerometer data, which we saw previously. The bottom graph will show the output of the LSM6DSV16X sensor's machine learning core engine. There are several lines plotted. We are only interested in the output of register 0, which is the red line. This is the output of the sensor's machine learning core corresponding to the three motion conditions that we trained. With the sensor held steady in your hand, the red line should output 0, corresponding to the stable condition. With some light movement, the red line should jump to 4, which indicates the movement condition, and with more intense shaking, the red line should be at 8 for the shake condition. This determination is happening inside the machine learning core within the sensor itself, and with no signal processing required on the host STM32 microcontroller. In a real-life situation, the firmware running on the STM32 host microcontroller could read this output at runtime and take appropriate action. For example, in this case, it might trigger an alert when the shaking condition is detected. You may see some noise in this graph, since this was a fairly quick example of training the machine learning core, and we did not do any in-depth cleaning of the training data. But in general, you should see a differentiation between the stable, movement, and shake conditions even with this quick example. You may now click the red Stop Log button at the top and close the High-Speed Data Log GUI. The data log package is just one example of what can be done in Pro mode. As we saw previously, there are also other function packs available that support the sensor tile. Many examples are available that illustrate various basic functions of the platform, and these might be useful for you to begin your own project. You may now close any other windows you may have open, including any Windows Explorer and command prompt windows used in this module. In this module, we used the SensorTile.box PRO in Pro mode, used the high-speed data log function pack as an example of what can be done with custom firmware, captured some real-time sensor data, and used it to train a machine learning model for the LSM6DSV16X sensor. This concludes Module 6.